I have a really packed agenda for you guys. I'm going to spend first few minutes introducing terminology, industrial Internet of Things, reactive systems, and a middleware for that called data distribution service, which is used for connectivity in industrial IoT systems. Much of the talk, nearly 45 minutes or so, is going to be about stream processing. And for that, we are going to use DDS for sending data between processes, and Reactive Extensions. It's an open source, specifically RxCpp, an implementation of the Rx programming model in C++ 11, C++ 14. On the right, what you see there is that's the demonstration, the application I will use for demos at the end. It should actually bounce. It was, right, for a second and then it stopped. I don't know why. Oh, now it did. Okay. That's fine. So what is industrial Internet of Things? It is basically the next big revolution in industrial revolution. So what are the things that come to mind when you think about industrial Internet of Things? Smart grid, smart transportation, smart hospitals, connected medical devices, connected cars, and those kind of things. Smart factories, really efficient sort of assembly lines, and those sensors, the sensors that are going to enable all this will be connected over digital networks, IP networks specifically, and will send data. They will communicate with each other and also to the cloud to get all this data and extract some value out of it. So much of the value that IoT hype, the classic, let's say, Internet of Things hype, is sort of is going to provide. Almost 80% of that value is going to come from the industrial aspects of it, not necessarily the thermostat that you may have at your home. So construction of these systems is actually pretty complicated stuff. In industrial IoT, they cannot stop processing information. They have to live within the world imposed timing. So this is, I'm talking about soft real time and sometimes hard real time requirements. There is a subset of systems that are relevant in IoT, industrial IoT, where computing happens at the edge of the system. It is called edge computing or fog computing. You may have heard of those buzzwords as well. Much of the data that is going to be produced at the edge in the systems cannot be and will not be sent to cloud because it's just too much data. And you really don't need all that data to be sent over to cloud for processing. Of course, you don't want to lose the insights that you may have at the source. So you process that data right at the spot, which is at the edge, and send sort of the summary data or maybe the insights that you may have to the cloud for further processing. And much of that data is also going to be push-based. It's going to come at you no matter what. You cannot really do much about it. So you have to be ready to handle that. So those systems have certain characteristics that you have to meet. Responsiveness. That means you have to be ready to react, and you have to react at the speed of the environment governed by the laws of physics. You have to be ready. They have to be resilient, very fault tolerant, and scalable. They should grow and shrink as the load increases or load goes away. To get these characteristics, event-driven design is the way to go. What that means is you have to have system components that are loosely coupled and they communicate with each other using asynchronous messaging. There is a name for systems that have these kind of characteristics, and that is reactive systems, essentially. You may have heard about Reactive Manifesto, a very interesting read. I would suggest you to look at that. Concurrency is another aspect of these systems which is very important. As it turns out, concurrency alone is not going to be sufficient. You need a programming model where on a single machine, when you have multiple cores, something that can make use of all the cores, and when scale grows, the same programming model should be able to make use of multiple machines when it needs to. something that can achieve that is very powerful. And we'll look at one such programming model today based on data distribution service. It's a reactive middleware. Everything that you see in DDS, things like any events or even application startup, application shutdown, some entities come and go, their lifetime, those kind of things, which are very important in real-time systems, those are all propagated as events. So you can react to them, not only just data, this is not just data, but even some extra information about that data, like there is a new application that will talk about a particular thing. I'll give you some examples later. DDS is a connectivity standard, as I said before. It's a simple publish-subscribe programming model, actually. So there could be streaming data, sensors, events that are published, and these publishing applications communicate with the subscribing applications at the bottom, and they don't really know about each other. They don't have to. That's what the asynchronous or anonymous communication means in publish-subscribe. So a few concepts about DDS communication model that will be useful later in the demo time. So there is this conceptual global data space. You could think of it as a database with tables, but there is no persistence. I mean, it is all in memory because it has to be real time and very fast. There are participants that connect to this conceptual global data space, and publishers and subscribers, they communicate through what's called topics that's in the middle. So a track topic, let's say, you have an air traffic control system, you have an aircraft that is coming towards an airport, and as it's, let's say, within 10 miles of the airport, it will create a beep or a dot in your radar. It will have its own lifetime. It will, the plane will approach the airport, it will land, it will taxi and whatnot. So it has this definite lifetime that your system is aware about. And something like that is done very well with DDS communication model. So those are tracks 1, 2, 3. You can think of, I don't know, Delta 1, 2, 3, 4 flight and some other flight that simultaneously there could be many of those. It's no different from your usual relational database model. Each has a key, and key identifies a row, and you could have thousands or millions of keys. Only difference is that the particular row will be updated really, really fast, potentially thousands of hertz at a time. So DDS is a standard family. This standard has not much to do with the C++ standard. It's an API standard in C++, Java. There is a wire interoperability standard. There is a web integration standard, a security standard. That's a big one. It's basically a stack with a whole set of technologies and implementations that are available. So when I got an opportunity to use DDS for a industrial Internet of Things system, I had a choice. Should I use the standard API or an awesome API, which is what I'm going to talk about. And this awesome API has a very distinctive flavor, and that flavor is what I think is reactive. Is the reactive part of that is very curious about that. With new language features in C++ as well as in Java, functional features have been catching up in mainstream programming. So with lambdas in C++ and Java, this style, the functional influence is growing. I think that's my point. And functional reactive programming is a particular application of that design style for asynchronous or stream processing. You may have heard of stream processing. It is basically a simple architectural style that operates on a continuous sequence of data. A very simple model to think about when you think of stream processing is, I think, or most people, I'm sure most people in this room are familiar with simple Unix command line pipes and filter. So you could create more complicated commands by chaining together these little command line programs together, right? grep and whatnot, cat, and you can create, you chain them together using pipes. So you conceptually thinking about each line will go through this pipeline, and I will drop some, I will process some, and I will get something at the end of the day. So that is exactly the same programming model that we are going to use in C++. although it's not line by line, is going to be any complex data structure or simple types, if you like. One part that I would like to focus is construction of in-memory data pipelines. This is related to the concurrency point that I made earlier. When you have a programming model that can create, let's say, multiple pipelines in parallel that can go concurrently, if there is no data races or there is no data dependencies between each other, all those individual pipelines could potentially be concurrently executed. And there are many applications, especially stream processing applications, that lend themselves nicely to this kind of shape, abstract sort of shape of an application. And your program almost starts to look like this, actually, at least one of them. And then if those arrows, right, if those arrows are asynchronous, you could choose to sort of split this diagram into two machines. On left-hand part maybe runs on one machine and right-hand part runs on another machine, provided the arrow is asynchronous, or you could choose to make it asynchronous. So I think visually that's how I think about it. Then what's that programming model? I think reactive extensions gives that flexibility of thinking about and designing systems. So this is something that was invented at Microsoft. I think it was about 2007-2008 timeframe when Eric Meyer and his team implemented the first version of reactive extensions in C#. And right now Microsoft actively supports and maintains, I believe, the .NET C# version and JavaScript. It's an API for asynchronous streams and composing them together, and that abstraction is called observable. And observable is actually extremely simple abstraction. It's almost unbelievable. I'll show you in a second. That's coming up next slide. How simple abstraction can actually, if it is composable, can build remarkably powerful. You can do remarkably powerful things with it. So observables are basically first-class streams, and by composition, I mean there are a whole bunch of different combinators, or let's say just library API, you could call it that way, for filtering and selecting data from those streams. These are asynchronous streams, right? So the data is coming at you and you don't have any control over it. You have to be ready. And you can aggregate the data, or maybe you could have time-based filters, so many things that you can do on that incoming data. The key to note here is that anytime you apply a function like a filter or map or whatnot, it gives you back another observable. It always stays within its familiar world of observables. It's not like jumping around in and out of that world. It is always an observable. So you see that example, several examples. And let's talk about concurrency. Rx has no opinion of concurrency, actually. It lets you process your data in a single thread application or multi-threaded application. You really don't have to do much different. The code looks exactly the same. The Rx contract ensures that much of the code that you write, you don't have to worry about locks and those kind of things. It's heavily relying on functional programming style, and it's available in practically every modern language that exists today. .NET, Java, JavaScript, C++, Ruby, Python, lots of them. So when Eric Meyer talks about observables, he likes to compare observables with essentially, let's say, the enumerator, which is same as the iterator concept in C++. So on the left, it's pull-based interface. As you know, in iterators or enumerators, you have to ask for information. You have to say sort of, okay, you have to dereference with a star in case of C#. This is, I think, the only C# code that I'm going to show, because it makes a lot of sense, because this is how the original design was. You have a move next operator, not an operator, a function on an enumerator, and it tells you if there are more samples or not. So you just keep going in a loop. If it ends, if move next returns you false, you end, and current gives you the current value, or it may fail. It may fail to retrieve that particular value from database connection. Maybe if the connection is lost, current may throw an exception. These three operations or concepts map really nicely to the push-based abstraction of observables. An observable is really a simple API that has subscribe. There's only one thing you can do with an observable. You can subscribe. You can say, hey, I'm interested in your data. I'm going to observe it. Here it is. That's all you can say. And what's an observable? What's an observer is, okay, there are three functions that you have to implement. If there is some data, it will call on next. If there is no more data and it ends in a proper way, in a tidy way, it's on completed, that will be called. And on error if there is an exception. Because potentially this code can be asynchronous. It makes little sense to throw exceptions like we do on stack. There is no catch and throw business here. Well, at least not on surface. We do that internally. But in general, you get your exceptions as a callback through on error. Now, believe it or not, this is exactly the dual of the pull interface. And there is an excellent video I would recommend you to watch. It's very heavy on theory, video on duality, where Eric Meyer and his colleague talk about how they can be derived one from the other using some really interesting mathematical properties. So you can always represent an array or a pull-based interface with a push. Only thing is that now data will come at you rather than you asking for the data. They are, in that sense, equivalent in their expressive power. If you put observable in a grid with async and, let's say, multiple value, that's where it fits. So an observable can produce optionally, asynchronously, 0 or more values, which is comparable to an iterator. Now, of course, there is a difference between push and pull. Perhaps you're familiar with an alternative asynchronous single value abstraction, which is a future. You register a callback with, say, .then or .next, and when the future is ready, the future is basically a type that will be either satisfied or may throw an exception little later. It doesn't have value right away. So you have to sort of say, hey, whenever this thing is ready, call this successive operation. And that's what the .then and .next API does. So observable is a generalization of it. Because observable can have 0 or more values, but it has to be, has to end, let's say. It doesn't even have to end. It could just go on forever. In some cases, there is no need for an observable to end. So this is very powerful because in most cases, and definitely in stream processing, you expect just infinite stream. The program just has to keep going and process data. So with that, we come to the first RxCpp example. So values is a simple observable of integers, and it's initialized with a range observable 1 to 5. This expression really doesn't do anything. It's not like there is an array or some storage that is going to contain all these elements 1 to 5. It only says, hey, all right, values is going to be from 1 to 5, but only if there is a subscription to it. If there is no one listening, then nothing really happens. So that means you have to add a subscription to this data, and you do that using a function called like subscribe. That is the pretty much only thing you can do with an observable. So you pass in 2 lambdas here. The first one is the onNext call, which takes an integer and just prints it, and the second one is onCompleted. So when 1 to 5, it's through 1 to 5 is going to call that. So the output you expect here is, shouldn't be a surprise, is just 1 to 5 on next and then on completed. It does it very synchronously, pretty straightforward. This is pretty much the simplest program. There is no asynchrony here at this point. We'll look at that in just a few minutes. So this is the basic programming model. You create an observable and subscribe. So between those two stages, when you create an observable, that's your true source, and before you subscribe, you can attach arbitrary number of, let's say, business logic or any transformations, a little more academic word here, between those stages. So range is same as before, and I'm going to map that each value that's going to come through this observable, through this function, it will be just multiplied by 10, and then filter if it's not, I guess, if it's divisible by 15, it's going to filter it. So map and filter are an example of the API I was talking about. Anytime you apply those functions, it results in another observable. So you can continue chaining those together. It's not the same observable, it's not a mutation, but it's a new observable that will do what you expect to do here. The original observable stays how it is, and map will give you a new observable. We don't have to sort of create a separate variable for that. You can just tag along more operations as you go and build your sort of data pipeline. So this tends to be a little more declarative. You are really saying what needs to happen to the data, just like you would do in Unix command line, pipes and filter, a same kind of operation. I guess filter would be not grep. I guess, yeah, you could think of it like grep, I guess. And then you subscribe at the end of it. So in this case, the output is 30 isn't printed because that's what got filtered. So original source up to map, it produced all the values, but then filter dropped one of them. So here is a sort of interactive marble diagram that shows you how map sort of works. So the top line is the source observable, and it produces values 1, 2, and 3. And the bottom one is the mapped observable, which produces values multiplied by 10. And as the values are sort of time axis, and the right hand side, the vertical bar indicates the end of the stream. So when the original stream ends, the derived stream also ends with it. Or when original stream throws an exception for some reason, it doesn't throw, it kind of propagates an exception. The bottom one will also do that. So that's the mental model. Rx Marbles has actually a lot of interactive diagrams like this. You can play with many of them. Sometimes it just works better than documentation actually. So here's an example of sort of asynchronous program. I couldn't make it any simpler than this one. So O1 is a observable that produces values every 2 seconds. And O2 is an observable which produces integer values and starts from 1 to 3 every 3 seconds. And they are independent of each other. So I want to combine those values together and do something interesting with it. And in general, there can be more than 2, of course, but this will give you an idea of how simple it tends to be to combine truly asynchronous observables. So values is the result of an operation called combine latest. I'll talk about that in a second. But before that, I want to transform O1 into characters. So I'll just add A, capital A, and turn it into a character. So it's the O1.map produces a new observable, which is observable of characters. And now I combine that with O2. What combine latest means is, this is just an example. You could, for every new value that comes through the first observable, it takes the latest value of the other one, combines them together, and by combine I mean it just produces a tuple and produces that out. And you can do anything, whatever you want with the latest values. You will have a guarantee that the values in the tuple are the absolute latest values that came through the whatever you are combining. So I'm going to take only 10 values because the original observables are infinite observables. They don't really end, modulo overflow, I guess. And just take 10 values. At the 10th value or 11th value, it takes away the entire pipeline and releases resources and everything. I subscribe to the values observable, which is going to be a tuple. Each value that is produced is a tuple of character, comma, integer. I print that, and the output of that looks something like that. I think the animated GIFs kind of stop in the middle. So anyway, I think you got the idea at the first few lines when those were printed. Every 2 or 3 seconds, depending upon which one works is ahead, it will print values, characters and integers together. So okay, it goes again, and that's how it keeps doing processing. I think you get the idea. So Rx4DDS is a library that's built on top of Reactive Extensions CPP implementation that uses RxCpp for processing DDS data. It's implemented in C++11, C# and JavaScript, and anything that is produced from a DDS sort of global data space, which is just normal data and even other metadata, so to speak, can be processed as an observable, because everything is going to be asynchronous. This gives a very powerful model to process that data. DDS is used for data distribution and Rx is used for in-memory processing. So on the left-hand side, so data readers bring data up to your doorsteps, and then Rx picks it up and does all the interesting processing with it, and may even produce some resulting data. We'll look at some examples. So the box in the middle is the single process. I think at architectural level, they are a fantastic match. That's because DDS has the publish-subscribe model, a distributed publish-subscribe model, and Rx has in-memory observable observer model, which is a sort of like publish-subscribe, especially when you use the subject, a facility called subject in Rx. The stream lifecycle, I touched upon this idea of a flight, and it lives for a small period of time. Let's say if it's going to land at an airport. That stream has a life cycle. The plane appears on radar, it lives for a while, and it goes away. That model maps really nicely to the Rx model of, hey, there is a new observable, it's probably going to say something, and then it will produce 0 or more values, and it will either terminate, or it will terminate in a good way or not so. So those concepts map extremely well, and that's why I think they work together nicely. So rest of the talk is about this shapes demo application. I'm going to use 3 different DDS topics: squares, circles, and triangles. You could think of them as anything that is producing values continuously. They can have multiple colors. The type that I'm going to use is shape type and has color, shape size, X and Y. And color is just like a database key or a table key. So when you talk about a blue square, you're talking about a specific row. And a red square is different from blue square. You're talking about different row, and each one will have its own update, each one will have its own life cycle. And we will be able to process it that way using in-memory data structures. So this is sort of, I think I should click play over here because this is an embedded video. This is just an introduction. Later on we'll see more interesting things. I want to make sure everybody knows how the setup is going to be. On your left hand side is the publishing application. It is going to, throughout the rest of the talk, is only going to publish information about, let's say, squares or triangles or circles, and that's it. It just says, hey, here I am, that's it. The right hand side application is going to subscribe to one of those, or maybe all of those, either a square topic, circle topic, or triangle topic. And if there is information about that topic, it will pick it up and it will just show you. The bottom one is where the transformations are going to run, the processing stages. And it will, what we are going to do is run some interesting transformations on incoming data from the left hand side, and it will go to the right hand side if it's already subscribed. So by now it should have created a square, I think. I hope it's going ahead. It's not stuck somewhere.
or maybe it was. Let me just click ahead and okay, there you go. So this time I'm going to create a blue square. There is a lot of configuration that you can do in this application, different quality of service for real-time systems. We are not going to need that anything today. So this is a blue square that is just doing its thing, bouncing around. And on the right hand side, I'm going to create a subscription for squares. Again, a lot of configuration, we don't need that today. And it should just pick up the blue square on the left. The small tail you see on the right is basically its history. You could configure it to be anything you want. That's a DDS feature that it can tell you last how many, whatever many places it has been. So if you need to know more than just absolute last value, you have it in your process. So similarly, there is a circle and a circle subscription. There is a tail there as well. I think you get the idea. I think this video goes on to create a triangle as well. So we don't have to necessarily go through that. So those are going to be the main things. So let me click ahead. Maybe I should click next. All right. So this is, I'm going to use this application to create effectively a solar system. So what kind of application do we want to build? So let's take a look at what the application needs to do and what kind of code you may have to write with Rx to achieve that. And I should click play here again. So you have a blue square on the left and it has been subscribed already to the right. What I'm going to do is produce a circle around this bouncing square. That's the transformation. So it's going to receive information of the square location and create a orbiting circle around it. And then what I just did there was a subscription of square, circles, and triangles. Because there was no information earlier, you didn't see anything. But as soon as I started the transformation at the bottom, it picked up the square on the left. The data went to the processing stage at the bottom and produced a resulting stream of circles and triangles. And they are sort of orbiting around each other. So there is a clear dependency here. The square has to, as square moves, the circle also needs to move, and it's circling around like a solar system would. So this is the sort of application I'm going to create. All right, so to start, you have to have a topic subscription. That's how you create data readers if there is a subscription. In this case, I'm going to subscribe to the square topic, and there are some other participant and wait set and a thread that you have to pass in for processing, but that's not important today. From this topic subscription of square, I'm going to produce an observable, which is an observable of lone sample of shape type. So what lone sample is really a simple type. It's essentially a reference type containing 2 pointers. One pointer looks at the data, shape type, and the other pointer is a lot of meta information about this data. In a sense, is this something new that you are looking at? Is this a new stream? Is this, if it's a blue or green, there is a time when it is new in the system, and that's when this metadata will say, hey, yeah, this is a new data that you're looking at, or at the end, right? Because it maintains the life cycle. If it goes away in a clean way, it is disposed or whatever, then it will also tell you that this is the last sample I'm going to tell you about this blue square, and no more updates. Do whatever you want with it. That is mostly clean up my resources, or in some cases, hey, this is really wrong. I mean, this is a nuclear reactor temperature monitor. Don't go away, please. You have to raise an error in that case. But you get that opportunity. So that those life cycle events can be mapped really nicely to Rx programming model. So that's what I'm going to do next. So on next, on complete and on error, give me an opportunity to map those sort of distributed stream components or stream concepts over here. So the source is the observable that we created, and then complete on dispose is sort of a stage that will process this incoming source of lone samples. And if it is disposed, that means it's an update, hey, this is no longer needed, it's gone, it will propagate it as a uncompleted event. The difference, of course, is the write shift operator. This is an extension to RxCpp, and you will tend to write a lot of extensions in your code because you're going to do your application specific processing. It does not allow you to say, dot complete on dispose, because dot, we cannot overload dot in C++. This is effectively the same thing. You can replace conceptually write shift operator with a dot, as if thinking like, okay, this is an observable, dot, do this transformation on it. The result is, of course, a new observable that will be, it will do the transformation as part of this operation. The next operation is if there are no writers, for instance, a nuclear, temperature gauge for a reactor, and somehow you just lose contact, you get isolated because of a failure, and there are no updates that you're receiving, your operator really needs to know that this is happening and something can be done. So you could raise an alarm or raise an error if there are no writers. Somehow you get disconnected. So it propagates an error, and it's up to you how to handle that error at the application level. This gives you an opportunity to translate that information into a programming model that is just flow of information. And then in some cases you may have wrong data. That wrong data should be filtered out, and in this case it's a filter operator, and I'm passing in a lambda that receives a lone sample and filters away everything that is not valid. So beyond this point, only valid samples that have good data in it are available, and I can map that to just data. So like I said, there are 2 pointers in it. One is data, so I'm just extracting data out. So the resulting observable, the square track, is now a good stream of data that is just pure values, no errors, world is sort of running smoothly if it succeeds up to that point. If it's the error path, that's not the case. So that's what the observable shape type looks like. Now we have to transform this and create circles and triangles. So this transformation is going to be stateful. So again, I'm going to apply map. So as you will find out, map is actually a really powerful concept in functional programming, and it shows up all the time in observables, even in arrays. If you know, the ranges library has similar concepts in it. And circle degree is how the state is maintained, and every time there is an update for the square, it will move the circle a little bit, a few degrees, and shape location is a function that will return a new value. So given a center of circle and some degrees, it will just give you a new position, and that's where I'm going to draw the circle. So you can see that it's very cleanly representing the dependency between the source data and the resulting data, and that is, I think, very important. The result of this is sent to a tap operator. The tap operator is just like, hey, there is a data flow, let me just tap into it and do some side effecty things with it. So in this case, there is a circle writer. I'm not going to talk about how it was, where it came from. It's created. It's a simple writer. It expects that writes to the circle topic, and for every single value that is coming out of this map, it will just write it out. Because there is an application that writes circles out, the subscribing application that we saw earlier simply picks it up and shows you. So far it's just a clean flow. A very similar transformation for triangles, because the triangles take each position of the circle and draw themselves. Exactly the same code, only difference is that this time I'm going to publish that information on a triangle topic using triangle writer. So note that this is a stateful transformation. So the value triangle degree is what the state is. Of course, you could have arbitrarily more complex transformations, stateful transformations in this process. So this is all the code that you need to write to produce the demo that we saw earlier, a single circle and triangle orbiting around each other. I think it matches the conceptual model, and you can see a flow of sort of the data flow right in your code. So let's look at some of the internals. Skip invalid samples, the filter operation that we looked at, could be implemented using C++ 14 lambdas like this. As the Rx contract goes, you have to create a callable that will take a previous observable, and you can apply whatever transformations you want and return a new observable. So what you're returning here is a lambda, or closure I should say. And what should that closure do when called? It applies filter. So it returns source observable applied to the filter operator, and the code is of course how to determine true or false, and the resulting observable is returned. I think auto kind of looks very succinct here, looks appealing at least on slides, but I'm not a great fan of auto in some cases. This is actually C++ 11 code written without autos. It's a different operator though, but pretty much the same. The types are spelled out. Actually, I like this style, even though this is quite verbose, because for a newcomer, and when you come back to your code 3 months later, you know what you're expecting, and types are good documentation. I'll comment on that towards the end. But of course, you can do this in both languages. All right, so I'm sure many of you have seen the Golden Gate Bridge. How many of you have seen this particular cross-section of the main cable? Have you been to that location where they have a few people? Interesting. So what you're looking at is a cross-section about 3 feet diameter. That's the main cable of Golden Gate Bridge. And each cable is actually made of more than 27,000 small steel cables. It's unbelievable how they constructed this main cable. There are 2 of them. They are essentially woven together, 27,000 of them or more. So it's like one giant cable of cables. I think that model of cable of cables is very relevant for the next demonstration, which is data pipelines. So earlier you saw just one sort of simple data flow, but now we want to replicate that data flow for each key. For a different key, we want to create a different circle, a different triangle, essentially sort of sharding of the keys, so that if there is no dependency, which is not in this case, they can go concurrently. So if you have 10,000 keys or 10,000 different sensors that you have to monitor or do something with it, then you can concurrently on a single application, on a single core. So as usual, to a square and its subscription, I'm going to subscribe to circle and triangle. You're not going to see anything because the transformation isn't running. So only when data is available it will show you. So that's how it gets stuck a little bit. So yeah, it's progressing now. And triangles, and let's run the transformation this time at the bottom. So you saw this already. This is just the blue square, nothing new here. But in a second, I think I'm going to create a green square. Let's see what happens after that. Bingo. So now you have a completely independent pipeline that is processing exclusively green things and a separate pipeline processing blue. And again, this is a stateful transformation. I guess the next one is yellow, but you get the idea. What kind of code you may have to write to achieve this? That's what the exercise sort of is, or a demonstration is all about. It's not just just recognizing the appearance of new square, new color, but also disposal of it. So if I get rid of one of those, what happens to the circles and triangles of that color? They should also disappear, right? Because they are no longer meaningful, because it's like, I don't know, if it's the sun, if sun goes away, what good is Earth going to be, right? So let's get rid of, well, I don't know, I think it's the blue square that I dispose it off from somewhere in the network, and it takes away everything from the transformation as well as the subscription, because it recognized that all the blue things got disposed of from the network. They are no longer relevant. They are cleanly removed from the system. And so the green ones also. Remember that only the original square was disposed, but the system was smart enough to recognize that everything else that depended on it was also cleaned in a very straightforward manner. If the green square comes back online, maybe it was a temporary disruption, it picks it up all over again where it discontinued. Of course, you have to write some code for that. It may be erroneous condition or maybe not, depends on your application. So what kind of code you may have to write for that? So again, topic subscription as before, and this time remember the analogy of cables. This is going to produce a group stream, group by instance. For each key, it is going to produce a new observable. So what you're looking at is an observable of observables. So each value that is produced by this outer observable is an observable itself, which you can subscribe to or dispose of, and it has its own life cycle and whatnot. And the key is that inner observable will talk about only blue things, or let's say only blue squares or only yellow squares. So that gives you a very good way of thinking. Hey, you can point at a particular object and say, okay, this is the blue guy, and let's do some transformation on it. Group stream type is rather mouthful. It's an observable of grouped observable that is keyed on string in this particular case, and of course lone samples. So you can ask the grouped observable, what key are you? Like, are you blue, are you green? And then you can maybe do a database lookup or whatever you want to do that is specific to blue or that color. So how can you program something like this? So we start off with the group stream, and we use the almighty Flatmap in this case. This is really sort of the holy grail of, functional programming, or really famous operator you will find in a whole bunch of libraries. It really has two components, right? There is a flat part and this is map part. So flattening is, for every stream that is coming in, the inner one, each sample is really an independent new stream. It simply merges all of them together. That's the flat part, the flattening part. So if you have, let's say, an array of arrays, you could think of an array that is just flattens out. It just takes each element, just flattens it out. That's exactly the same thing. Only difference is that the data is coming at you. That's the flat part. What is the map part? Well, before simply partitioning them out in multiple keys and just merging them together, that's like no op, right? It's like, why would you do that? It gives you an opportunity to attach some transformation to each incoming stream. And that's what the Go argument is, which is a group shape observable of, for each new key, there's going to be a new Go value. And I'm going to do some transformations, actually exactly the same transformation before, because now I know that Go is a specific color and a specific stream that I am looking at. So I got rid of the key part of it. I don't need the key, I will use it a little later. Complete on dispose, the same semantics again of error handling and dealing with the completion of a stream. Skip invalid samples, we looked at that. Map samples to data, which is pure data. Then map to circle track, because squares, this is the stateful part. Then publish it over DDS, because that's how the subscribing application will get it. Map to triangle track, this is the same thing again, and that's basically it. you basically took the earlier program that you wrote right in the middle of it, and the Flatmap operator will now subscribe to each of this transform stream one at a time as it is produced, and simply subscribe to it. So you don't have to subscribe to each stream that's coming in. Flatmap will do that for you. And then you subscribe only one, which is the outermost one, which is the cable of cables. And that's it. You have to maintain only the outer subscription. Inner subscriptions, there could be thousands, they would be maintained automatically by Flatmap. The way the inner code looks, I think I have to say I love it, because it is literally prose, and it says what you mean. It's a transformation. It happens for each key, and there are no loops as such. In a sense, it's very declarative in its sort of expressiveness. So I think this is a very interesting example of how you can do stream processing over multiple keys. So now you could have created new threads inside, or maybe inside for each go you could have used a thread pool or whatnot, so that you could partition your incoming keys and its processing on a, I don't know, a 4-core machine with 4 threads or whatnot. That becomes an add-on, a very separate modularized idea that you can just simply introduce over here if you want. It's not necessary, of course, because in this case it's going to be completely single-threaded execution of all the streams that are completely asynchronous. You don't know when data is coming, but it will just do the right thing. All right, and that brings me to the last demonstration, sort of a dynamic correlator. I would encourage you to tell me what it is perhaps trying to do. So here's the demo. I think I should click play over here. And as usual, blue subscription, and I ran the program right away, and it shows a triangle. And let me create a green square this time. Any guesses? What do you think it's doing? What kind of transformation is it? Come again, please? Average. It's average, exactly. It's averaging the values that are coming in for each key. And it doesn't know how many keys there are going to be. It's dynamic in a sense. As many keys are there going to be, it will just pick them up as they come in. It's very reactive in that sense. And when I put all those original squares at the corners, you see that the triangle sits right in the middle. And then it's, of course, the average of all the values. So what kind of code you might have to write to do something like that? And turns out it's pretty straightforward. Although there are some new operators that you have to build. I'm not going into the details of that. So the earlier example is what the earlier first code is, first half of the slide. I'm going to do a map, not a flat map this time, because for each inner stream, I have transformed it as usual. But of course, no triangles and no circles this time, because I just want to create an average. So up to map samples to data is the same code as before. And the incoming stream is again stream of streams. For each incoming stream, it produces a new stream. And I'm going to coalesce them. All the alive streams, I'm going to coalesce them together and produce a vector of all the active streams. So this is an operator. It's a custom operator. It doesn't come with RxCpp when I last saw. It's basically taking a snapshot of all things that are alive. So it basically makes a vector. The resulting observable is a vector of observables. And you are guaranteed by this operator that each observable is active. It has not completed. It is not erroneous. The point is that you can create really arbitrary combinations of these transformations and just tag along different transformations. Sure. So coalesce alive, like I said, produces each value is a vector of observables. I want to map that. So sources, let's say at a particular instance, at some point we had 4 active streams, right? So all those 4 streams are put here in observable, and then in a vector, sorry, and so sources, and I'm going to call combined latest on that. So if you think about it, combined latest takes latest value from each, and this time there are 4 of them, let's say, is going to take latest values of all 4 and just combine them together. It's going to produce this time not a tuple, but a vector, because the number of elements could change at runtime. There could be 1,000 elements or 1,000 streams that are active at a time. So each value that is produced by combined latest is a vector of values. And that's what the map transformation does. Of course, we have to subscribe to that. When we get a vector of all the values, all you have to do is just average them out, right? And just print it or publish or what have you. But there is one trick though. There is one thing that has to happen. Anytime there is a change, if there is a new stream that comes to life, or maybe one of them goes away, the vector should shrink and grow, right? Because it's no longer alive. So let's think of the case where it's going from 4 observables to 5. You have subscription of earlier 4, it produces the 5th one. Now you have to sort of get rid of the earlier 4 and subscribe to the new 5 or the new vector that you get. That's what switch on next does. For each new stream that is, okay, switch on next works on stream of streams. Every time a new stream comes in, it unsubscribes the old one, subscribes the new one, and just keeps doing that. It just kind of, it's really fickle-minded. So it's like, okay, forgets the old one, when it finds a new shiny thing, it jumps on that. And that is exactly the semantic we want here, because anytime there is a change in the subscription, I want to throw away earlier average essentially and start building a new average with new set of streams. There could be, by the way, more than one streams that could go away or come to life, right? It doesn't have to be one at a time. Everything is asynchronous. You have no control on how things may turn out. So map is just at the end, this map is guaranteed that the shapes is a vector of values that is the absolute latest values of all alive streams. And you just calculate average and you just print it out or dispose or show it using DDS. So a fairly complex transformation, this is literally all the code that you have to write to get a very powerful reactive multi-core aware a location transparent code that reads just like prose, no locking. The key is, in all this code there is no locking actually that you write. There are of course the operators that take care of that asynchrony, but you don't have to worry about that. I think this becomes a really powerful model because of that. So that's basically it. Based on my experience of using functional programming C# and C++ and JavaScript, really those are not functional languages, but they are the mainstream languages. I think functional programming in C++ tends to be quite noisy. Lambda capture, you have to say, at least according to Scott Meyer, you should specify what you want to capture and not just default capture, not use that one. Mutable adds an extra layer of complexity, whether it's going to change it or not change it. The most vexing point is, I think, that lambdas don't extend the lifetime of what they are capturing. If it's just a pointer, you are toast. You have to create a shared pointer. If you are passing multiple on-next and on-completed lambdas, they all have to share the same state. You are better off creating a shared pointer in the class and share that one. That's sort of a restructuring of your code. I think that is starting to become like a pattern, at least in this implementation that I've been in Rx for DDS. Too much auto, like I said, could be very problematic. It's not readable when you come back to that code. Compiler errors could have given you error much earlier if you had a type, but it doesn't. I think if you have them already, please don't remove them. Types are great. They are good, not only for the compilers, but for human readability. And if you want to learn about RxCpp, but you do not know Rx, I would strongly recommend the other flavors of Rx first, because C++ brings its own complexity, like really long type names. There are some alternatives to deal with, like as dynamic. So that's basically it. Actually, I have some resources that are online. Number of resources have been written so far on Rx for DDS. There is a research paper. If you want to look at, you can take a look, and RTI. So that's basically it. If there are any questions, now would be a good time. Sure.
So do you recommend, or are you trying to make RxCpp real-time safe, like useful locking? Then, like the user provides a thread model, right? Like you said, there's internal locking.
Yeah.
Is it real-time safe, or like suited to solve real-time?
The question is, I think, is the locking model in Rx implementation or Rx for DDS, whether it is real-time safe? And I think if I understand the question correctly, whether it honors priorities of real-time processes and those kind of things. I don't think that's the case. In an operating system that supports priority inversion protocol or those kind of facilities, perhaps there is a way to re-implement the locking in RxCpp implementation. I think that would be one way to do it. But I think by default, RxCpp uses the standard library capabilities. It has no dependencies other than standard library. So if standard library does it on your platform, then it will just borrow those capabilities automatically. So that might be one way of doing that. Sure.
And maybe picking up the question, how much overhead does the framework have? So assuming I just would run on one core on a single machine and just would use it for processing some streams, how much overhead do I have in between all those filters and transforms?
Right. The question is, what's the overhead of this programming model? Now, I don't have exact numbers for you. I think the best answer is benchmark. That's the safest answer. But I can tell you this. In RxCpp, the model is, there is not necessarily dynamic dispatch. You have to opt in, let's say, virtual function dispatch. There is all the code that you saw today does not use dynamic dispatch. If you use as dynamic, that means you're going to do that, which is going to have more overhead at every stage, for every sample. For processing a single integer, you may end up doing multiple dynamic calls, which is not going to be performant. But when you avoid those, then you can rely on the bits of compiler to coalesce all the code into as efficient, optimized code as possible, because it has visibility through all the types, all transformations and everything. So I would say it is going to be very performant as long as you stay away from certain operations. Although they are useful in some cases, like they simplify types, because it's type erasure essentially. So types look simple, but then for release version, you could perhaps get rid of as dynamic or virtual dispatches.
So when you put in a lambda, it stores it in a state function, or is it aware of the type and compile time?
I think it is aware of type. There is no, the question is whether lambdas are stored in state function. My answer to that is no. The RxCpp implementer is right here with us. Perhaps you could comment.
They're not stored in standard function unless you introduce as dynamic.
Excellent. So that's, so Kirk just commented that they are not stored in state function, because that would automatically make it type erasure and a dynamic function call. Yep, question?
So my question is, do you guys do any benchmarks into how does that compare to more traditional parallelized graph processing model? But I think I really like the concepts and the ideas, but I really want to know the performance impact of the real-time. Is
Yeah, I think the question is how does the performance compare against real-time graph processing?
Yeah, just a parallel graph processing, multi-threaded distributed graph processing.
I'm not familiar with programming model that supports that. I could tell you this, that C# implementation that I used for performance comparison, actually a high throughput experiment, I was able to achieve on a single laptop, this very laptop, about 250,000 samples of say 50 bytes each. So 250,000 samples per second on a single threaded application per second.
Yeah, that's actually
250,000 samples in C#.
that's actually quite slow.
For some applications, it might be the case, yeah. Or a different implementation like RxCpp perhaps. That was sufficient for our needs for at that time. It's turned out to be okay. Any more questions? Yep.
I guess I'm probably not quite the target audience for this, but I've used a few things like TPP flow graph and things like that on a single box process, multiple threads, but not distributed physically. Are there like simplifications to this? Like, do you need the DDS part if you're running on a single box, but you still want to have the streams part of it?
I think the question is DDS needed on a single machine?
You know, to what extent is this like all or nothing, basically?
I see. This is an integration effort. So DDS is not required to use RxCpp or any flavor of Rx. My experience is using DDS for stream processing or distributed stream processing using Rx. So that's why I combine those two things together, and they make a lot of sense. But in a single application, you could just use Rx by itself. I would say this though, if you have a Rx-based application and now you want to distribute it with sort of the same conceptual model, DDS might be an excellent choice for that distribution because it keeps the same model of stream lifecycle and asynchrony across machines, publish, subscribe. So remember the data pipelines diagram where each one of those arrows, if you want to actually split it open and make it distributed, you could insert DDS over there and partition your data that way. Any more questions?
I have one. Slide 48.
Sure. Yes. Is that the one? Yeah.
Yeah. Since we have a network of concurrent things that's reactive, how come there's no risk condition when you're passing references to your lambdas there?
A reference to the lambda. Okay, the question is.
This is as argument to lambdas, in both cases of vectors, because you're taking the latest values, but they could change. So why?
Right, excellent point. The question is, I'm passing in, I guess, in both map functions, there is a reference to the source, the vector. Right. This is the result of on next, right? I mean, on next will give you this value in map. The Rx contract says that on next is never interleaved. Anytime when there are multiple updates that are coming at you, on next will never be called at the same time on two different threads or asynchronously. So over here, I'm guaranteed by the implementation of map that the source vector it's looking at is basically protected by a lock internally, which you don't see here, but that's the contract in short. Yep, question?
Rx libraries for other transport protocols like MQTT?
Good question. I think question is Rx library available for MQTT and other transports? I'm not aware of any implementation, but it shouldn't be hard to create. So that probably means it already exists. Somebody has probably done that. It's just you can plug in any source of data you like behind to power an observable. So it's possible. definitely possible.
Right shape, it's just a matter of whether there's a supported project for it.
That's right. All right, that's great. Thank you very much.